Have you ever wondered how the universe, with all its complexity and vastness, could have emerged from nothing? And if this idea challenges everything we know about the laws of physics? The creation of the universe is a question that has intrigued scientists and philosophers for centuries. How could something so vast and complex have emerged from nothing? The concept of nothing is difficult to define and understand. It is almost like asking what is north of the North Pole. The universe, with its galaxies, stars, and planets, seems to defy the notion that it could simply have appeared from an absolute void. This mystery continues to challenge the laws of physics and our understanding of reality. Thinking about the origin of the universe is confronting the unknown. Many people claim to know exactly how the universe began, but without concrete proof, these assertions are merely speculations. The most accepted theory, the Big Bang, suggests that the universe began as a singularity, a point of infinite density and temperature. This singularity rapidly expanded, giving rise to the cosmos we know today. But where did this initial singularity come from? This is one of the great enigmas that still need to be solved. The Big Bang not only marks the beginning of the universe but also the birth of space and time. Before this event, the concept of before loses all meaning, making it irrelevant to ask what existed before the Big Bang. This raises fascinating questions about the nature of time and space and the very laws of physics that govern our universe. As we delve deeper into these questions, we begin to explore other theories and possibilities about how the universe could have emerged from nothing. Admitting the unknown is a crucial step in the quest to understand the creation of the universe. It is important to recognize when we do not know something because it opens doors to investigation and discovery. Often, people make unfounded assumptions about the origin of the universe, claiming to know its nature without concrete evidence. The truth is that without proof, any theory is just speculation. The Big Bang Theory, for example, although widely accepted, is still a hypothesis based on indirect observations. The Big Bang Theory suggests that the universe began as a singularity, a point of infinite density and temperature that rapidly expanded. But even this theory encounters limitations when faced with the unknown. The singularity represents a state where the known laws of physics break down, making it extremely difficult to understand events preceding or at the singularity itself. Recognizing these limitations encourages us to continue exploring and questioning, without taking anything for granted. Recognizing the unknown leads us to question the nature of the initial singularity and what preceded it. If the Big Bang was truly the beginning of everything, where did the energy that triggered this cosmic explosion come from? There are theories that suggest states prior to the Big Bang, such as the inflation theory, which proposes a rapid expansion before the main event. However, these hypotheses are also shrouded in mystery and uncertainty. The Big Bang Theory is the most accepted explanation for the creation of the universe, suggesting that everything began from a singularity. This initial point of infinite density and temperature rapidly expanded, resulting in the formation of all the space, time, matter, and energy we know. During this process, energy was converted into subatomic particles, which eventually formed atoms. This event marks the beginning of all the cosmic structures we observe today, from galaxies to stars and planets. The initial evolution of the universe was marked by several significant epochs. Starting with the Planck epoch, which lasted from 10 to the minus 43 to 10 to the minus 36 seconds after the Big Bang, where the laws of physics as we know them did not yet apply. This was followed by the Grand Unification epoch, from 10 to the minus 36 to 10 to the minus 32 seconds, where the fundamental forces began to separate. The inflationary epoch, from 10 to the minus 32 to 10 to the minus 12 seconds, was a period of extremely rapid expansion that shaped the structure of the cosmos. These initial phases were crucial for the formation of the universe in its current state. As the universe expanded and cooled, energy was converted into matter and antimatter. These annihilated each other, but a small amount of excess matter survived, forming the first atoms. This process culminated in the quark-gluon plasma epoch, from 10 to the minus 6 to 10 to the minus 4 seconds, and the formation of hadrons, from 10 to the minus 4 to 10 to the minus 2 seconds. From there, the universe continued to evolve through the epochs of leptons and photons, leading to the formation of the first atomic structures. Singularities are true enigmas for scientists because they represent points where the fundamental laws of physics break down. In a singularity, like the one that gave rise to the Big Bang, gravitational forces are so intense that our current understanding of space and time loses its meaning. Before the Big Bang, the concept of time as we know it simply did not exist, making it irrelevant to ask what was before this event. This is one of the most challenging and intriguing questions in modern cosmology. The initial singularity of the Big Bang raises fascinating questions about the nature of time and space. How can something emerge from a point where known dimensions disintegrate? The laws of physics that govern our universe do not apply within a singularity, creating a paradox about the very existence of the universe. This initial point, where all dimensions merge into one, challenges our understanding and forces us to consider new theories and models that might explain this primordial phase of the universe's creation. Beyond the physical questions, singularities also raise profound philosophical problems. What does it mean to exist in a state where time and space are not defined? This mystery fuels debates about the nature of reality and the essence of the universe. Some theories suggest that our universe might be just one of many in an infinite multiverse, where each singularity gives rise to a new cosmos with its own physical laws. The inflation theory is a fascinating proposal suggesting that the universe underwent a period of extremely rapid expansion before the Big Bang. This theory was proposed to explain the uniformity of the large-scale universe and solve problems like the homogeneity and isotropy of the cosmos. During this inflationary phase, which lasted from 10 to the minus 36 to 10 to the minus 32 seconds, the universe expanded exponentially, smoothing out any initial irregularities and creating the foundation for the cosmic structure we observe today. Cosmic inflation explains several observed features of the universe, such as the uniform distribution of cosmic background radiation. Without this phase of inflation, it would be difficult to understand why distant regions of the universe appear so similar to each other, given that there was not enough time for them to exchange information. This theory also provides an explanation for the critical density of the universe, suggesting that it is incredibly flat and homogeneous due to the rapid expansion that occurred in its initial moments. However, the inflation theory also raises new questions and challenges. What exactly caused this rapid expansion? And what happened before the inflation? Some scientists suggest that quantum fluctuations in the vacuum could have triggered this inflationary phase. Others propose that inflation is part of an eternal cycle of creation and destruction of universes. To better understand these possibilities, let's explore the idea that the universe may have emerged from a quantum fluctuation in the vacuum. The quantum fluctuation theory proposes that the universe could have emerged from a quantum fluctuation in the vacuum. In quantum physics, the vacuum is not an absolute empty space but a field of minimal energy where particles and antiparticles are continuously created and destroyed. These temporary fluctuations in energy can, theoretically, give rise to entire universes. This idea suggests that our universe could have emerged from one of these quantum fluctuations, providing an alternative explanation for the creation of the universe. Quantum fluctuations are temporary changes in the amount of energy at a point in space, resulting in the temporary creation of particles and antiparticles. These pairs of particles usually annihilate quickly, returning to the vacuum state. However, under certain conditions, these fluctuations can become stable and expand, potentially giving rise to a new universe. This theory aligns with quantum mechanics and offers a way to conceive the creation of the universe without violating the laws of physics. Despite being intriguing, the idea that the universe emerged from a quantum fluctuation raises many questions. How exactly can these fluctuations create something as vast and complex as the universe? And what specific conditions are necessary for a quantum fluctuation to stabilize and expand? These mysteries continue to challenge scientists, but the theory offers a fascinating perspective on the origin of the universe. Quantum mechanics is one of the most revolutionary areas of physics, describing the behavior of subatomic particles in terms of probabilities and waves. According to this theory, particles like electrons and photons can exhibit both wave and particle behaviors simultaneously, depending on the experiment conducted. This duality is fundamental to understanding how particles behave on very small scales and is essential for the theory of quantum fluctuations that could have given rise to the universe. One of the most famous principles of quantum mechanics is Einstein's equation, E equals mc squared, which relates a particle's energy to its mass and the speed of light. This principle suggests that particles can be created and destroyed in pairs, such as electrons and positrons, as long as the total energy is conserved. This constant creation and annihilation of particles in the vacuum is what makes quantum fluctuations possible, offering a basis for the idea that the universe could have emerged from such events. Quantum mechanics also predicts the existence of virtual particles that spontaneously appear and disappear in the vacuum. These virtual particles can become real under certain conditions, such as during the rapid expansion of the primordial universe. Quantum uncertainty, which allows the position and energy of particles to be unknown precisely at the same time, opens the possibility that quantum fluctuations can generate entire universes. This quantum fluctuation model offers an intriguing explanation for the creation of the universe. The quantum fluctuation model of the universe suggests that uncertainty in a particle's position leads to uncertainty in its energy, allowing for the temporary creation of particles and antiparticles. This phenomenon, predicted by quantum mechanics, is known as vacuum fluctuation. According to this theory, in a moment of high energy and density, a quantum fluctuation could have expanded uncontrollably, resulting in the creation of our universe. This idea offers a fascinating explanation for the origin of the cosmos without resorting to external causes. During these quantum fluctuations, Heisenberg's uncertainty principle plays a crucial role. This principle states that it is impossible to simultaneously know the position and momentum of a particle with absolute precision. On a quantum level, this means that the vacuum is never truly empty but is filled with fluctuations that can, under certain conditions, generate enough energy to create matter and antimatter. These spontaneous creations form the basis for the hypothesis that the universe could have emerged from one of these fluctuations. The idea that the universe emerged from a quantum fluctuation is both provocative and challenging. It suggests that our universe is just one of many possible realities that can emerge from fluctuations in the quantum vacuum. This also implies that the laws of physics as we know them emerged along with the universe, being products of these fluctuations. To better understand how this relates to the Big Bang theory, let's now explore how cosmic inflation integrates with this quantum view of the universe's beginning. The cosmic inflation theory proposes that the Big Bang was preceded by an era of extremely high energy density, causing a rapid and exponential expansion of the universe. This inflationary phase, which lasted only a fraction of a second, was crucial in establishing the initial conditions that led to the Big Bang. Inflation explains the uniformity and isotropy observed in the universe, resolving problems that the Big Bang theory alone could not solve, such as the homogeneity of the cosmic background radiation. During inflation, the universe grew from a subatomic size to something immeasurably large in an instant. When this inflationary era ended, energy was converted into matter, antimatter, and radiation, resulting in the Big Bang. This process not only shaped the structure of the universe but also established the foundation for the formation of galaxies and other large cosmic structures. Cosmic inflation also suggests that the universe may be much larger than the observable part, with regions beyond our cosmic horizon that remain unexplored. Integrating cosmic inflation with the Big Bang theory offers a more complete and robust view of the creation of the universe. Inflation explains the origin of the quantum fluctuations that expanded to form the large-scale structure of the universe. These fluctuations are the seeds of the galaxies, stars, and planets we see today. However, many questions about the origin of the universe remain unanswered. Despite advanced theories like the Big Bang and cosmic inflation, many questions about the origin of the universe remain unanswered. The idea that the universe emerged from nothing is particularly intriguing and difficult to reconcile with our understanding of the laws of physics. If space, time, and matter did not exist before the Big Bang, how could something arise from nothing? This concept challenges not only physical laws but also our most basic intuitions about cause and effect. The notion of a universe arising from nothing implies that nothingness itself may have properties that allow for the spontaneous creation of everything we know. This leads us to question whether we truly understand what nothing means in a cosmological context. In quantum physics, the vacuum is not an absolute void but a dynamic field where particles and energy can appear and disappear. Could it be that nothingness, in a cosmic sense, is a state with infinite potential for creation? These ideas force us to reconsider the foundations of the laws of physics. If the universe can arise from nothing, then our theories about space, time, and energy need to be re-evaluated. This does not necessarily mean that the laws of physics are wrong, but that they may be part of a more complex and profound structure that we do not yet fully understand. This mystery continues to drive research and scientific exploration. Conceptualizing a state of absolute nothingness is a challenge, both philosophical and physical. In philosophical terms, nothingness is the opposite of existence, a total absence of anything. However, in modern physics, especially in quantum mechanics, nothing is more complicated. The quantum vacuum, often considered nothing, is actually a field of minimal energy where virtual particles are constantly being created and annihilated. This suggests that nothingness can be a potential source of creation. The very theory of cosmic inflation also complicates our understanding of nothingness. It suggests that before the Big Bang, there was a state of rapid inflation that erased any information about a pre-existing state. This means that even if there was something before the Big Bang, inflation would have eliminated any evidence of that something. Therefore, our conclusions about the initial state of the universe are limited to what we can observe and test in the current physical reality. Despite advances in cosmology and quantum physics, the nature of nothingness remains an enigma. Can absolute nothingness truly exist, or is it always a state of latent potential? The idea that the universe could have emerged from nothing challenges not only the laws of physics but also our fundamental understanding of reality. These mysteries encourage new investigations and theories and keep debates about the origin of the universe alive. And so, we come to the end of this fascinating journey through the origin of the universe. We have explored how theories like the Big Bang, cosmic inflation, and quantum fluctuations offer possible answers about how it all began. The idea that the universe could have emerged from nothing challenges our most basic notions about the laws of physics but also opens us up to new and exciting possibilities. What we learned today is that science is constantly evolving, always seeking to understand the deepest mysteries of the cosmos. The notion that the universe could have emerged from a quantum vacuum or a fluctuation in nothingness not only intrigues us but also inspires us to continue exploring and questioning. Curiosity is the driving force of discovery, and every answer we find leads to new questions and new horizons. If you enjoyed this video and want to continue learning about the mysteries of the universe, don't forget to subscribe to our channel and turn on notifications. That way, you won't miss any of our upcoming videos. Join us on this incredible adventure through space and time, and let's uncover the secrets of the cosmos together. Until next time.